Okay, so hello everybody. My name is Fabian Peller, and I'm from KIT, working with Tamim Asfour at the H2T lab. And I would like to present the platforms of KIT which we have. So I will skip the institute part because this is a technical meeting, so I will only talk about the platforms. And yeah, I will show you, for example, the humanoid robot Armor 3. The Kautz humanoid head, the humanoid robot Armor 4, the humanoid robot Armor 6. So you see that we are focusing on humanoid robotics. The KIT XO1. So we are not only doing humanoid robotics, we are also doing exoskeletons and prostheses. We're also focusing on that, and on TERRINet we also offer our human motion recording platform, as well as our Now robot. So we have a bunch of Now robots which we also offer. And finally, because these softwares, most of them share the same software framework, I will explain how to use the software ArmorX and what ArmorX is about. So I would like to start with the robotic platforms. First of all, we have Armor 3, which is a humanoid robot. It's actually currently our oldest robot which we have in the lab. I think it's pretty well known. It's working in a kitchen environment, which is also part of the platform. And yeah, here you have some technical information. So the robot has several degrees of freedom. It has pneumatic hands. It has an holonomic platform, so it is able to move in every direction. It has laser scanners, so it is possible to avoid obstacles. And yeah, it has a weight of 150 kilogram. So these are the technical data of this robot. And additionally, I will show you a few applications which we do with this robot, so that you get an insight what is possible using that platform. So first of all, I would show you a video about your combining vision, action, and haptics. So it's part of the your interactive vision or active vision problem, where the robot should find out in a cluttered scene what is an individual object and how to grasp that object. You're using simple techniques. So here we have the point cloud. We have some clusters, and by pushing to the scene, the robot finds out what is the cluster of that point in the scene, so that it's finally able to grasp it. Another thing which is very which is a lot of research done at our institute is grasping in general. For example, here we have deep grasping, but we are also focusing on normal grasping, PCA grasping, for example. And yeah, this is also a topic which we are really focusing on. So grasping with a humanoid hand, and not only a gripper, but a humanoid hand, which is much more complicated than just using grippers. So here, for example, Armor 3 should grasp the salt and then lift it and so on, and then pour it to the object. Another thing which is very well researched at our topic, or which we focus on, is programming by demonstration. So we have a demonstrator, a human, for example, and when we ask the human, or when we ask the robot, can you, for example, prepare dough for me? Then the robot knows some actions. But for example, here we have a mixing motion, which is not available to the robot's memory. So it doesn't know what is mixing. But from observing the human, he knows that mixing is quite similar to cleaning or to wiping. So the robot is able to use the same motion for the mixing motion, and this puts the robot into another direction. So it's not just a robotic platform, but it's somehow a cognitive platform, because it's doing cognitive tasks. For example, replacing actions. But these are not the only applications we are working on. So there are also a lot of more. We have reusable skills for the robot. We are learning from sensory motor experience. So the robot has a lot of sensors in it. We are learning from object affordances. We try to extract those affordances from the scene. We try to automatic generation of planning domains, so the robot is able to plan and so on. So these are just a few of the research topics. Another platform of the TERRINet project is the Karlsruhe humanoid head, which is mostly used on Armor 3. So this is a standalone platform, but it's also used on Armor 3. And here you have some technical data. So it has 4 DOF in the neck. It has 3 DOF in the eyes. Here it has more than just one camera per eye. So this is also important. It has a lot of microphones. It has an 60 inertial sensors, so an IMU, and several cameras. Like I said, 4, not instead of 2. And yeah, so this is the technical information about that platform. And using that platform, you can do, for example, interactive vision, or not interactive vision, but vision problems and so on. So the next platform is Armor 4, which is the only legged robot we have at our institute. So all the other robots have an holonomic platform, or the other humanoid robots. And yeah, it's torque controlled. It has 3 embedded PCs inside. It has a lot of microcontrollers there, a lot of CAN buses, or six CAN buses. It has 63 DOF, which is quite a lot. Again, pneumatic-driven hands. Yeah, and the weight is very, very lightweight for that platform. And of course, it also has a bunch of sensors. So you can do a lot with it. For example, haptics or vision, or yeah, it depends on your imagination. So what we done with Armor 4 is mostly in the context of push recovery, using, for example, yeah, the DF system of the robot, or stepping. And this is one of the work we done with Armor 4. So when pushing the robot into a direction, the robot should decide whether to make a step or not, and we created a measure for that using the zero moment point and COM, when to make a step and to what direction to make a step. Okay, so the next platform is our newest platform, which is Armor 6. This is a humanoid robot, which is very, we put all the experience we had from the other robots into that robot. So as you can see here, it has an one DOF here to increase the height of the robot. It can grasp things. And here's some technical information. So it has 27 DOF. So we have 2 DOF in the hands, 8 DOF in each arm, 14 DOF in the hand, but it's under-actuated. So we have 2 motors here, one for the thumb and one for the other fingers. I will explain in detail with the next platforms what about the hands. 1 DOF in the torso, and we have 4 wheels. So again, it's an holonomic platform. And the weight is 160 kilogram. And what's really cool is that it has a really great payload. So you can like this carry 10 kilogram, and like this about 14 or 16 kilogram. And this is very, very special. We did it very, very modular, and we created those sensor actor units. So they also made at KIT, which are used for the whole robot. And the good thing about this is that we only have one cable from motor to each other motor using Ethernet, and of course energy. And we have 3 sizes. So here is a bit information about the sensor actor units, which you can see here. Yeah, so we have three sizes: size S, size medium, size large, which differ in the configuration. Okay, so also the working range of the robot is very great. So we have very big arms of the robot. It is able to grasp things from the ground. It is they're a bit taller than most humans are. Yeah, and the torso joint or the prismatic joints allows the robot to lift objects from the ground, for example, or to work with humans when putting things up. And here's a small video about the application of Armor 6. So this was at the CeBIT in Germany, where we did the demo, I think, about 50 times, something like that. And this is a demo from the second-hand projects we are working in, where the robot should collaborate with the human to disassemble this your conveyor belt you've seen there. And we implemented several applications. So here, for example, we have kinesthetic teaching using zero gravity compensation, and the robot is able to avoid or to recover from disturbances. I think I can increase the video a bit. Yeah, as you can see here, the robot is able to do by manual grasping, so it can carry heavy objects. We're implementing DMPs on the robot, so it's able to be torque controlled, velocity controlled, position controlled, of course. Yeah, these are some tasks we are doing with it. And I think so. You can see it's this is some heavier object because there are some tools inside, as you can see. So and of course we are also working in the context of grasping. Like I said before, or reactive grasping. This is an older video, so since now we have improved that feature of the robot, and it's also able to lift objects which are really near the table, for example, a torch or cloth or whatever. And this is the second-hand demo I explained before, where the robot is able to help the human. So here we have a human on the other side, which is lifting down this guard of the conveyor belt, and the robot is able to recognize if the human needs help. So when the human is under the conveyor belt, the robot should be able to help the human. And of course, it should be able to work with the human. So this robot is made for collaborative work. Sorry. So this is the demo we are doing. The next platform we are working on is the KIT Exo-1. So this is an exoskeleton for the lower limbs. And this exoskeleton has two motors. One is here, one is here. It has a maximum axial force of 3,000 Newton, maximum nominal force of 930 Newton, and a speed of 100 millimeter per second. So it is able to help people working, but we are focusing on augmenting exoskeletons. So this is not an rehabilitation exoskeleton, but an augmenting exoskeleton. And what we are doing with it. So what's the special thing about that exoskeleton is that we are not using electrodes on the human skin, because that is mostly a problem, because electrodes are somehow noisy and you have to adjust them every time, and that's why we only have here 4 sensors and IMUs on the exoskeleton. And using that, we are doing motion classification, motion prediction, to let the exoskeleton recognize what the human is doing and what the human wants to do. And like I said, we are also working on hands. So these are just a few hands we developed at KIT, and the newest prosthesis is also part of the TERRINet platforms. So we developed a prosthesis, and the cool thing about that first is the mechanism, which is described here. This is the mechanism of the first hand, which is quite old, but it's still cool, because the force gets distributed over all fingers. And if you block one finger, there's only one motor for all those fingers. The force gets distributed using that mechanism, which is called intelligent mechanics. And again, here's some technical data. And another cool thing for prosthesis is that we use a camera here. And using this camera, we can react to different kind of objects. So if the if the user wants to grasp a specific object, sometimes the prosthesis have to do some pre-grasp. And using conventional prosthesis, this is very hard to configure, because the wearer has to pre-shape the hand somehow, and this is some semi-autonomous way to do that, which is called your embedded camera for vision-based semi-autonomous grasping. And again, here's a video. We also developed some self-experience shaft, where your normal users can try to use this hand. And here you can see how the hand uses a pre-shape motion. So it first pre-shapes the fingers so that you can put the fingers into the handle, and then it closes the hand, for example. Here. As another platform is our human motion database we have. So we have a Vicon system consisting of 14 cameras. 4 of them are Vero cameras. So if you want to do very short distance recordings, for example, for grasping. And we store all the recordings in a database, which is publicly available. I think it's one of the biggest, or the biggest publicly available database of motions. And we have a capturing size of 6 times 4 meters. And the goal is to put motions from the human to the robot. And we've developed some technique to segment those motions. So here we have the KIT taxonomy to segment motions into important frames. So whenever you have contact to your environment, you can segment the motion, and using this taxonomy means that interacting with the environment is the same as grasping, because the environment grasps the human here in this case. And this means that we can analyze the motions done in the motion recording. So we also offer this reference model of the human body, which is called MMM framework. It's basically using markers. So we have the markers on the human doing the motion, and we have markers on a reference model, this one, and we are doing nonlinear optimization to fit this model into the motion framewise to get this your animation. And using the taxonomy I explained before, we can analyze such motions and then put them to the robot, for example, as shown here. So the human is doing some complex gesture, and then it's first put to the human reference model, then it's put to the robot reference model, still in simulation, and then to the real robot. So here as our last platform, we also have the Now robots, which are quite popular. So I won't go into detail here. So this is just the Now platform. This is, by the way, the only platform which is not using ARMA X. So of course the YCon system is using Nexus, but the MMM framework we use after that again is using ARMA X, which I'm going to explain now. So we have our software framework, which is completely developed at KIT. So it consists of it's used on the ARMA Robot series, like I said. It has we offer bridges to other platforms. For example, we have a YARP bridge for the IPCAP model, and we are currently working on a generic ROS bridge, so that you can use ROS inside of ARMA X, and that you can communicate to ROS and from ROS. And it's an environment for developing complex robots software systems. Going from, for example, low-level motor control to high-level planning. So we developed all that stuff for the robot. So as you can see here, we have the low-level layer of ARMA X, which are sensor observers, sensor actor units, and so on. We have the mid-level, which is the robot components, the robot memory, which is very important, the perception system. And then the high-level control of that system. And what's very important for TERRINet is also that there's everything we do here is open source, so you can try it out. And we have a documentation online using Deoxygen, and we have code tutorials. So you can do the tutorials to learn how to work with ARMA X on our homepage here. And your ARMA X below is using Series CIs, which is a very widely used framework. And using that, we can send messages for distributed systems. So we have a lot of systems in your ARMA X. So we have the ARMA X core, which is providing the ICE interfaces and so on. We have the robot API, we have robot components, a GUI to interact with the robot. We have the memory X consisting of prior memory, working memory, long-term memory, and so on. Vision X, also all the complete vision pipeline and obstacle avoidance and that stuff. We have robot skill templates. We have state charts, which is pretty cool because you can just drag and drop state charts for the robot and combine state charts to new high-level skills for the robot. And of course, we have the bullet-based simulation of the robot. All our robots are using Ubuntu 18, so we switched from Ubuntu 16 to Ubuntu 18. The tutorials are still available for both operating systems. And you don't, like I already said, you don't have to use the robot directly. So we also offer a simulation platform, bullet-based, where you can send commands to the robot, where you can do motion planning or all that pattern recognition of objects and so on. So as dependencies for our software, we mostly implemented the software on our own. So we are not using ROS nodes, for example, but the ICE and the ARMA X interfaces. But we have, of course, some generic dependencies. So like OpenCV, TensorFlow. So the very general things, point cloud libraries, Eigen3 vectors. Here, just to inform you what skills are required. And ARMA X is completely written in C++, but we also offer Python interfaces, so that you can use the ICE interfaces from Python over ARMA X, and all those components I explained here are written in C++. So C++ is a must-have if you want to use ARMA X. Yeah, so here are some links to our software, to the tutorials, to important papers about our platforms. You can use the first link, and of course we have the platforms on the TERRINet homepage. So I'd like to thank everybody, and now I'm open for questions.